Hello, my name is Suhas Arehalli, presenting joint work with Tal Linzen, titled Neural Language Models Capture Some, but Not All, Agreement Attraction Effects. Let me start with the phenomenon of subject-verb agreement. In standard American English, subjects must agree with their verbs in number. For example, in the sentence, "The key to the cabinet is rusty," both the subject, whose number is determined by the noun key, and the verb, is, are singular, and thus the sentence is grammatical. If, instead, I showed you the sentence, "The key to the cabinet are rusty," you could easily identify the sentence as ungrammatical. However, despite the relative ease of identifying this particular sentence as ungrammatical, numerous studies have shown that participants will make more agreement errors when an attractor, a noun phrase whose number does not match the subject's, is present. In this case, the presence of the plural noun cabinets makes it more likely that subjects erroneously produce or accept a plural verb like are, despite the subject being singular. This phenomenon, called agreement attraction, provides a window into the mechanisms underlying real-time sentence processing, allowing us to observe in what circumstances those mechanisms might fail, and produce or accept otherwise ungrammatical sentences. As such, agreement attraction has been studied extensively in the psycholinguistics literature, finding numerous factors that affect the degree to which the presence of an attractor increases the rate of attraction errors. Unfortunately, no current model proposed in the literature is capable of elegantly accounting for all of the findings. In fact, many generate no meaningful predictions for many of the experiments conducted. In this talk, we'll attempt to leverage the power of modern neural network models from natural language processing to address this issue. Much recent work has investigated the linguistic capabilities of neural language models, neural networks that are trained to take in a sequence of words from a corpus and produce a probability distribution over the next word in the sequence. One type of language model, a long short-term memory model, or LSTM, has been shown to be able to reliably compute subject-verb agreement, as well as display some human-like patterns in the distribution of agreement errors. It's important to note that LSTMs are general-purpose sequence learners, with no language-specific inductive biases. This combination of facts, the number of diverse agreement attraction patterns exhibited by humans, as well as the ability of simple neural language models to successfully compute agreement, leads us to two major questions whose answers we believe will allow us to better understand agreement processing in humans. First, what agreement phenomena in the literature will simply emerge from a general-purpose sequence learning model, which here will approximate with what phenomena an LSTM language model can learn. And second, what inductive biases might we need to give a neural language model in order to have it exhibit human-like processing? In the work I'll be presenting today, we'll primarily aim to tackle the first point, attempting to characterize what agreement attraction results in the literature an LSTM language model captures. Of course, by doing this, we'll also additionally gain insight into a third, related question. What strategies might these models use to compute agreement in the first place? In the paper, we present and discuss the simulations of the experiments whose results are listed here, but due to time, I'll only be presenting the first three, all of which focus on the role of syntactic and surface form position in agreement. Now, in each of these experiments, human subjects participated in a sentence completion task, where they were given a preamble like "the key to the cabinets" and are asked to complete the sentence. These responses are then coded for the rate at which participants make an agreement error, here producing are instead of the grammatical is. We simulate this by first training 5 LSTMs on 80 million words of Wikipedia. We then feed each model the preamble provided to participants in the human experiments, getting out a probability distribution over the next word. From this distribution, we take the probabilities of a candidate singular plural pair, here all either past or present forms of the verb be. We normalize their probabilities and consider the model's response to be a sample from this distribution. This differs from past agreement testing paradigms, which typically take the model's response to always be the more likely form. I'm happy to talk more about this difference in the Q&A. The first simulation I'll talk about today is that of Bach and Cutting 1992, which compared attraction effects from attractors within relative clauses, like singers in the demo tape that promoted the rock singers, with those from attractors in prepositional phrases, like singers in the demo tape from the popular rock singers. First, I'll present the results in humans, taken directly from Bach et al. 1992. In this plot, the y-axis will represent the percentage of attraction errors, the x-axis will represent whether the attractor was in a prepositional phrase, a PP, or a relative clause, an RC, and the two colors represent whether or not the noun phrase in the attractor position matched or mismatched the number of the subject. Here are the results. Note that what we care about is the size of the attraction effect, which is the difference between the blue and the red bars. And the crucial result here is that the attraction effect is significantly larger for the prepositional phrase attractors than for the relative clause attractors. Now here are the simulation results from the LSTMs. Each dot represents a single model's results, while the bars represent their average. Again, we can see that the attraction effect is significantly larger for the prepositional phrase attractors than for the relative clause attractors. And thus we find that prepositional phrase attractors are stronger than relative clause attractors in both humans and our LSTM models. Next, we'll consider a simulation of Frank et al. 2002, which compares the effects of the linear and syntactic distances between an attractor and the verb position. Participants are given preamble subjects with a doubly embedded prepositional phrase structure, the threats to the presidents of the companies, such that the first attractor is linearly further while syntactically closer, as in the dashed red line, while the second attractor is linearly closer but syntactically further from the verb position, as in the dotted red line. Thus, if there is a greater attraction effect for the first attractor, syntactic distance is a larger factor in the size of the attraction effect than linear distance, whereas if the second attractor has a larger effect, the reverse is true. Linear distance is more important than syntactic distance for attraction. On the left are the results in humans, taken from Frank et al. 2002. Here, the x-axis represents the mismatch between the first, syntactically closer attractor and the subject, while the two colors represent the mismatch in number between the second, linearly closer attractor and the subject. Thus, the crucial finding is that the main effect of attraction from the first attractor on the x-axis is greater than that of the main effect of attraction from the second attractor, represented as the difference between the two colors. Here are the results of our LSTM simulation, again with the dots representing individual models and bars representing averages. Here, the effect of the first, syntactically closer attractor, represented across the x-axis, is smaller than the effect of the second, linearly closer attractor, represented as the difference between the two colors. Note that this is the opposite direction of the effect in humans. While our LSTM models are subject to a stronger effect of the linear distance, humans exhibit a stronger sensitivity to syntactic distance. Finally, we're going to explore the role of linear distance independent from syntactic distance in Haskell and Mcdonald 2005. Here, participants were given a preamble where the subject was a disjunction where the disjuncts did not match a number. The disjunction's order was varied, so that in one condition, the plural disjunct was closer to the verb position, and in the other, the singular disjunct was closer. I.e., can you ask Brenda if the boy are the girls, or can you ask Brenda if the boys are the girl? These are the human results from Haskell and Mcdonald 2005. The x-axis represents the ordering of the two disjuncts, while the y-axis measures the rate of plural verbs produced by participants. The crucial result is a significantly higher rate of plural agreement when the plural disjunct is closer to the verb position. Now here are the LSTM simulation results. There are two things I'd like to mention here. First, the difference between the conditions is significant, and the effect goes in the same direction as humans. The rate of plural agreement is higher when the plural disjunct is closer to the verb position. The second is that despite the significance, the size of the effect is much smaller in the models than in humans, meaning that even though the effect is both significant and in the right direction, we can't quite say that the model's behavior is human-like. So, while the LSTMs are subject to a linear distance effect in the same direction as humans, the effect in the LSTMs is much smaller. So what do these three simulations tell us? Well, let's return to our original questions. First, what phenomena emerge from LSTMs, our proxy for a general-purpose statistical sequence learner? Well, we saw weaker attraction effects from within relative clauses than from within prepositional phrases in our simulation of Bakken-Cutting 1992. We did not, however, find effects of syntactic distance over those of linear distance when simulating Frank et al. 2002. And though we did find weaker effects of attraction from linearly distant NPs when simulating Haskell and Mcdonald 2005, the size of the effect was much smaller than was found in humans. Now, what might this tell us about how LSTMs compute agreement? Well, the pattern of results exhibited by LSTMs match the predictions of a proposal in Bakken-Cutting 1992 called the clause packaging hypothesis, which, in this context, roughly claims that the relevant syntactic measure is not the number of nodes passed on a parse, but rather the more coarse-grained notion of the number of clausal boundaries between an attractor and the verb position. The more clausal boundaries, the weaker the attraction effect. To spell that out a little more clearly, when we discussed the syntactic distance effects in Frank et al. 2002, we considered the distance between the attractor and the verb in terms of the number of nodes on the path between them in the sentence's syntactic tree, hypothesizing that the more nodes that lie between the attractor and the verb, the weaker the attraction effect. Under the clause packaging hypothesis, however, what we should count is not the number of nodes on that path, but rather the number of clausal boundaries that we cross. Nodes that don't represent a clause do not weaken the attraction effect. Note that this kind of effect is consistent with a system that doesn't have syntactic representations more sophisticated than simply marking those clausal boundaries. Now, this matches with the PP versus RC simulation results, since an attractor in a relative clause must cross a clausal boundary to get to the main clause verb, while a prepositional phrase attractor does not. Combined with the linear distance effect observed in the Haskell and Mcdonald simulation, this coarse-grained notion of syntax also explains the results of the Frank et al. Simulation, where there are no clausal boundaries separating the two attractors, so the difference in the attraction effect is only determined by the difference in linear distances between the two. Now, these observations point towards a potential direction for answering our final question from earlier. What kinds of inductive biases might lead us to more human-like processing? These results serve as an additional piece of evidence suggesting that in order to capture processing phenomena like agreement, we need models with stronger hierarchical inductive biases. In this case, such biases could serve to provide a more fine-grained notion of syntactic position, so these models can better capture effects of syntactic distance, like those in the results of Frank et al. 2002. In summary, we have simulated 6 agreement attraction experiments from the literature, 3 in the paper that I haven't mentioned today. Of those experiments, we found several in which the models were able to simulate, at least to some degree, the effects exhibited by humans, suggesting that these effects may emerge naturally from a simple statistical sequence learner, and thus would not require a specific cognitive theory to explain them. On the other hand, we also found several results that these simple models cannot simulate, which point toward more sophisticated models that could exhibit more human-like behavior. We see this investigation of the inductive biases necessary for neural network models to exhibit human-like performance as a promising direction for further research investigating both agreement attraction and language processing more broadly. Thank you.